Have you ever stopped to think about how your computer is even possible? I mean, right now you might have music streaming, a dozen tabs open, and you're maybe typing in a document, all at the same time. It feels like magic, doesn't it? Well, it's not magic, but it is a brilliant story of innovation, built up one clever solution after another. So how did we teach a piece of silicone to juggle? Let's dive in and find out.
Here's the plan. We're going to trace this whole journey in 6 steps. We'll start with the idle brain problem, move into how we actually interact with computers, uncover the art of the switch, and then look at the rules that make it all work, all the way to multitasking when lives are on the line.
Okay, so our story kicks off way back in the early days of computing with a really expensive problem, a super powerful brain that was just sitting around doing nothing.
So picture this. You have this ridiculously powerful and expensive brain, the CPU, that can just blaze through calculations. But here's the catch. It spent most of its time just waiting. Literally just sitting there twiddling its digital thumbs for a super slow printer or punch card reader to do its thing. It was like owning a Formula One race car, but only ever driving it in a traffic jam. A huge, colossal waste of power.
So the first brilliant idea to fix this was something called multiprogramming. And the logic is actually really simple. If a chef is waiting for water to boil, they don't just stand there staring at the pot, right? No, they start chopping vegetables for the next dish. That is exactly what multiprogramming does. By loading a few jobs into memory at once, the CPU could instantly pivot to another task the moment the first one got stuck waiting. The goal was simple: keep that expensive brain busy 100% of the time.
Now, multiprogramming was a massive win for efficiency. The computer was finally busy and happy, but it created a whole new problem for the people trying to use it. They were still stuck on the sidelines.
See, this was the era of what's called batch processing. You'd literally hand over your stack of punch cards to an operator, they'd run it in a big batch with a bunch of other jobs, and you'd come back maybe hours later to pick up your printout. There was absolutely zero interaction. You couldn't fix a typo, you couldn't check your progress. If you made one tiny mistake, you wouldn't find out for half a day. We desperately needed a way to have a conversation with the computer.
And this is where time sharing completely changed the game. It took that idea of switching jobs and just put it on hyperdrive. The goal wasn't just to keep the CPU busy anymore. It was about keeping people engaged. The system started switching between tasks so mind-bogglingly fast, we're talking hundreds of times a second, that it created this incredibly powerful illusion.
This image just illustrates it perfectly. The CPU is just cycling through everyone's tasks, giving each person a tiny, tiny slice of its attention. But it does it so quickly, in milliseconds, that to every single user, it feels like they have the entire computer all to themselves. It's a beautiful trick, and it's the foundation of basically every modern computer you and I use today.
Okay, so this brings us to the real magic trick at the heart of all this. We know the computer's switching super fast, but how does it pull off the sleight of hand so flawlessly, thousands of times a second?
I mean, that's the multi-million-dollar question, right? How can you just pause a program in the middle of a thought, let a completely different one run for a bit, and then come back to the first one like nothing ever happened? Well, the answer is a blisteringly fast and precise procedure. It's called a context switch, and you can think of it like a chess grandmaster playing a dozen games at once. When the buzzer goes off for one game, the OS instantly takes a perfect snapshot of that chessboard, where every single piece is. It files that snapshot away, pulls out the snapshot for the next game, sets the board up exactly as it was, and then makes a move. All of this happens so fast, the second process has no clue it was ever even on the bench.
The secret ingredient to that whole magic trick is something called the process control block, or PCB. The absolute best way to think about it is like a digital bookmark. For every single app that's running, the OS keeps this super detailed bookmark. When it switches away from your browser, it doesn't just forget about it, it carefully places a bookmark in the PCB that notes, okay, you were right here on this line of code thinking about this exact thing. When it's the browser's turn again, the OS just flips open to that bookmark and everything is exactly as you left it.
So now that the computer can do this amazing context switching, a brand new question pops up. Who gets to decide when to switch? Do we trust the programs to play nice, or does the operating system have to lay down the law? This led to two totally different approaches.
So on one hand, you had cooperative multitasking. This is kind of like the honor system. The OS just trusts that every program will do its thing and then politely hand over control so somebody else can have a turn. Then, on the other hand, you have preemptive multitasking. This is the strict parent model. The OS is the boss, it gives each program a tiny time slice, and when that time's up, boom, the OS preempts it. It yanks control away and moves on to the next program, whether the first one was done or not.
Yeah, that whole polite, cooperative model had a fatal flaw, and this quote just nails it. All it took was one badly written or malicious program to decide, you know what, I'm not giving up control. And just like that, it could hijack the entire computer, causing a total system freeze. And that is exactly why every major operating system today, Windows, Mac, Linux, you name it, is preemptive. We learned that for the whole system to be stable, the OS has to be in charge.
All right, so now we have all these programs running at once, taking their turns like they're supposed to. But this creates a new kind of danger. How do we stop them from, bumping into each other and scribbling all over their neighbor's work?
The solution is called memory protection. Basically, the operating system acts like a super strict security guard. It gives each program its own private, locked room inside the computer's memory, its own address space. And with help from the computer's hardware, it enforces one simple, unbreakable rule. You stay in your room. You can't mess with your neighbor's stuff. You can't even peek inside their room.
And if you've ever seen this error, a segmentation fault, this is exactly what's happening. It means a program broke that rule. It tried to access memory outside of its own little room. The hardware immediately sounds the alarm. The OS steps in, shuts down the offending program, and throws up that infamous error. It's the computer's way of saying, nope, you're not allowed to go there. But what happens when you just run out of those locked rooms? I mean, what if you have too many programs for the amount of RAM you have? Well, the OS has one last trick up its sleeve: memory swapping. It's like having a tiny desk, that's your RAM, and a giant filing cabinet, that's your hard drive. When your desk gets too cluttered, the OS cleverly takes the projects you're not actively working on and moves them to the filing cabinet. Yeah, it's a little slower to get them back, but it lets you juggle way more tasks than could ever fit on your desk alone.
So far, we've pretty much been talking about multitasking for convenience and efficiency. But what about those situations where the timing isn't just important, it is absolutely life or death critical? This is the world of the real-time operating system, or RTOS. On your laptop, if a YouTube video buffers for an extra second, it's annoying, but that's it. For an RTOS, a delay of 1,000th of a second could be a total catastrophe. The number one goal of an RTOS isn't to be the fastest, it's to be 100% predictable. A task must finish by its deadline, no exceptions. If it misses the deadline, it hasn't just been slow, it has failed completely.
And just look at where these systems get used. We're talking about air traffic control, surgical robots, a car's flight control systems, even a heart pacemaker. In these jobs, almost on time doesn't cut it. A single millisecond of delay could be the difference between a routine procedure and a total disaster. This is multitasking where failure is simply not an option. So, there you have it. From a simple trick to save some money on expensive hardware, multitasking has evolved into this incredibly complex, invisible dance that pretty much runs our modern world. And it leaves us with a really fascinating question to think about. As our watches monitor our health and our cars start to drive themselves, what do you think is the next great multitasking challenge that we're going to have to solve?